Google, DeepMind.
Exposed.
OpenAI. Secrets.
As ever, the world of AI is one that just keeps pushing the limit. Well, thanks to the guys at OpenAI and their O1 model, it seems as though the rest of the AI world is looking at creating models that think before they respond, just like the aforementioned O1 model. Looking to create an AI model that thinks at the level of a PhD holder, the guys at Google's DeepMind have come up with some new research that looks to make use of this method and break it down. Some say that this was done in a bid to demonstrate how scaling LLMs in the way that we used to in the past may not have been the best approach. This takes us to the ways these large language models were developed in recent times. When you take a look at LLMs, such as Claude 3.5 Sonnet and GPT-4, we have all seen how such tools became so powerful. Users were certain that these LLMs were able to generate human-like text among other compelling tasks. With their functionality, it is no surprise that a new standard has been set for these AI models. As great as this is, we have had to accept that something has to give as we chase the incremental progression of these AI models. You see, as these models become more advanced, they also seem to become more resource-intensive. As a result, these models become larger and more complex. This in turn requires more and more computer power. Those who work with these AI models will find that the more computer power these AI models need as they become more and more complex, the more money is going to be needed to maintain the entire system. Add the fact that there is also a need for more energy consumption and greater latency, especially when these models are being released in real-time or edge environments, and you'd find that maybe it may not be such a great idea to keep on with this increase in the size of these LLMs. Test time computing. It is such sentiments that created the notion of optimizing test time computing. This approach avoids the need to train a model to have a general grasp of all topics. Rather than creating such a model that would need to get larger over time, these developers figured that it may be better for these models to perhaps be smaller ones that think longer or more effectively during inference. This is great for those who get excited about the prospect of making use of these AI models in practical settings where such resources may be limited, but at the end of the day, performance still matters. This is exciting stuff because when you look at it, test time computing can be defined as the computational effort that such models may use when generating outputs, rather than when it is still in its training phase. One would find that test time computing is so important because when you look at it, popular models like GPT-4 are made to be big so that it can have a better chance of scaling up when the time comes. As we mentioned earlier, there are quite a few cons when one makes use of such an approach. You know, the rising cost and the use of tons of energy, just to mention a few. With such issues, developers were forced to think outside the box. What if they created models that were not so huge? This now left them with the question of if they could get the same level of performance, maybe even more, if they didn't scale the model itself. This is where these developers came up with the idea of optimizing test time computing. They figured that if they were able to allocate computational resources more efficiently during inference, there is a good chance that they would be able to improve their model's performance without the need to make it bigger than it is already. Even though the previous approach has proven to be successful in the past, this may just be the way to go forward, especially if users want to make use of a more efficient and a more cost-effective model. Sure, scaling up and increasing the parameter of your model may be the best thing when creating a model that may be able to handle extremely complex tasks that may need a ton of power to handle, but over time, test time. Computing may be the best way to go forward, especially when people just need a model when handling small tasks or when one may not have the power and resources to make use of the more powerful AI models. DeepMind research. With these concepts in mind, we can now look at the two main mechanisms that researchers and developers use to scale up computation during the model usage phase, without actually needing to scale up the actual model. Verifier reward model. The first approach seems to be a separate model that evaluates or clarifies the steps taken by the main LLM when it is looking at the answers to the user's problems or tasks. As such, users would find that rather than just generating the results and moving on to the next tasks, this model makes use of several possible outputs or answers before the verifier helps it find the best answers out of the bunch. As such, Users can say that this separate model acts like a filter that goes through each option before picking the final answer, after figuring how great it may be. With such a process in play, users can attest to how, as this model evaluates each step in the process, it becomes more accurate over time by making sure that each and every part of the reasoning process is working perfectly. Using such an approach, the developers and the users may find that this proves that an AI model does not need to be huge for it to be smart. All it needs to do is to make sure it has a good system that could help it check its work. This can be done by making use of these Verifier reward models. This will make these systems faster and more accurate, almost like the more popular AI models out there, without being just at large. Adaptive response updating. In contrast to the use of a separate AI model to make sure that it is coming up with the best answer for the user, people would find that adaptive response updating seems to feel like the user is allowing the AI model to adapt and refine its answers based on what it learned over time. You see, when the model is given a bit of a difficult task, models that make use of this approach would find that instead of just shooting off some answers on the fly, the model reviews its response several times. During this process, the model considers what it got wrong and what it got right in its past attempts so that it can focus on giving the user the best answers in the most efficient way possible. This allows the model to come up with better answers over time without the need of extra pre-training. This is really amazing because it gives users a Model 1 that ponders on tasks before giving detailed answers instead of always giving off one answer every time. Compute optimal scaling strategy. When both models are brought together, developers find that this creates what is known as compute optimal scaling. As complicated as this may sound, all this means is that we have to be tactical when it comes to how we make use of computing power. Rather than making use of a fixed amount of compute for all the tasks that it comes across, models that make use of such strategy make use of their computing resources in a rather dynamic manner that seems to be based on the difficulty of the task or prompt at hand. That way, you'd find that if the model is giving an easy problem, it may not use as much of its computing energy as it would have if it was dealing with a more complex task or prompt. When facing these more difficult models, it may make use of either the Verifier reward model or the adaptive response updating strategy to come to their results without needing to scale up. This is far different from the use of fixed computation strategies that most of these traditional models use today. These traditional models use the same amount of energy and computing resources for pretty much every task and over time that could make it less efficient than these newer, more adaptive models that we see today. Hopefully, these new systems of adaptive computing and reasoning would be the way to create even better forms of AI models in the future.